Hello everyone, so welcome to my channel again. So in our previous videos, we already talked about how we can construct a linear regression models, and then how we can use the hypothesis test and the confidence interval to help us to check about our assumptions of linear relationship and check about our estimators. So in these videos, we will talk about adequacy of our regression models. So that means we will talk about some assumptions of our linear regression models. And also later I will talk about something about our sum of the squares. So let's first look at when we want to construct a linear regression model, what assumptions of our model. So of course the first one is how we can write our models, right? So in this one, we always write our linear regression model as the beta is equal our y is equal our beta 0 plus beta 1x plus our error term. So here, of course, here for our data, we have the pair of data, right? So for each of our xi, we will have a pair of yi. And also based on this, we can compute our epsilon I as our error term. And then this is a first assumption. And then the second one is we always have some assumption of our error term. So here for our error term, generally we say we assume this error term is have a mean as 0 and the variance as a constant. And also we have the uncorrelation relationship between different value of our error term. So let me write the mathematical equations for these three terms. So this is the three equations for our second assumption for our error term. And then the last one, actually this one is still about our error term. But we generally have this one when we do something about hypothesis test, about our confidence interval, or in the prediction interval. So when we do this, because we need talk about the distribution about our errors or the distribution of our beta. So then for this one, we need a distribution for our error term. So that means here, normally we assume this is follows a normal distribution. And because in the previous assumption, we already said this error term has a mean 0 and variance as sigma. So that's why here we can write this as a distribution of normal distribution with mean 0 and the variance is constant, denoted by sigma square. So this is the three assumptions we normally have when we do a linear regression model. So then the next thing, what we generally have more assumptions. So the other thing is about our residual. So for our residuals, of course, in our previous videos, when we talk about ANOVA, we also talk about later about this residual analysis. But here I want to write a little more about this. So for our residual, the difference with residual and our error term, in this one it means now we already have some estimator of our beta 0 and beta 1. So that's why here the residual is a difference between our yi and the height of yi or yi hat. So, but the idea is for our residual, it should still about some errors, right? And then that means we still want this. It satisfies the second and third assumption of our linear regression. So that means for our residual, we have it also follows a normal distribution, and it also have a mean is equal 0 and the variance is a constant one. And then for different I, then we want the residual is also have some uncorrelation relationship. So this one, if now what we can do is, if we want to check about the normal distribution, then in our previous lecture, we also say this one means we can use some plot, the probability plot, to help us check the data is follows a normal distribution or not. So here, let me write down this one. So this is about our how to check about the normal distribution or not. So here, let me first draw a quick graph of this one. So when we try to get a plot of the probability plot, what we will have, we will of course first have a line here. So this line is about our normal distribution, so like this. And then for our data, we will have the data as some marks. So here for the data, we will have, for example, a data here, there, and there. So this is about our data. And then what we want to check is we will visually to check about this data. So if our data looks like a straight line and very close to our this black line, then that means we can say, okay, so it looks like a normal distribution. However, if we have some data like very far away from this line, then if this is the case, then we will say, okay, it looks far away from our normal distribution. So here, if you want to know more details, so please look at my previous videos and notes about how we can construct a probability plot and how we can analyze this, or say we can explain this probability plot. So this is about to check the assumptions 3 about the normal distribution. And then about the assumption 2 to check about mean variance and ion correlation between our EI. What we should do, we should also plot our EI. So here what we can plot is we will plot our EI with respect to our maybe YI or maybe XI or maybe just as order like the I. And then for here, what we will have is we should look at the graph of our EI. So if this EI looks very evenly, and this should evenly for the both sides of our horizontal x-axis. So because if it's above the x-axis or the horizontal axis, it means this we will have a positive value, right? And then this will means our true value y is larger than our estimator y hat. And then if this one is in the negative part, then that means this we get a negative value. So it means our yi is smaller than yi hat. So that's why here it should be the plot of our EI should looks very evenly. So we should also have the positive one and the negative one. Our estimator shouldn't be a biased one. So like only have a larger estimation or only have a smaller estimation. So this is about what we should have or what the plot should looks like. So now let me change another color, like maybe a blue one, to give some maybe green one, to give you some pictures, mock pictures about which one is a good and which one is bad. So first, we work on something the graph looks good. So here I give an example. So now we draw our plot of our E with respect to our X. So then we will have a plot looks like this. So for this one, we can see, okay, this one looks very evenly. So we have several numbers above the X, several number below our X, but we cannot, it's very everywhere. Maybe have a point. This is not focused on small area or not, or just in one side of the horizontal axis. So this is a good example. Then for the bad example, of course, there are different ways for it to bad. And then let me first give one bad example here. So let's look at this one. This is our first example for a bad bad E is a residual. So here for this one, it's very clear for our E with respect to X. We can say this is, we have a curve here, right? Looks like this. So what this curve means? So it means if our X is not too large or too small, then our estimation of Y will have a larger number. So what this means? This means yi minus yi hat is a negative value, like here. So this negative value means will have our yi hat is larger. So that means when x is between this area, we normally have a larger estimation of our y. And then if our x is very small or very large, like this area or this area, then we will generally have a positive e. So in other words, our yi is larger than our yi hat. So that means our estimator of y will normally have a smaller estimation. So this is means for our residuals, or in other words, for our linear regression model, this is a not good one. So in some part we have our estimation is too small. Some other part we have estimation is too large. So it's not good. So this is a full example for a bad plot. And then for the second one, let me see. So this is our second example. So what we can see here is we can very clearly see here when our x is become larger, for our e value is also become larger, right? So what this means? This means if we use our model, linear regression model, then when we try to get an estimator of y with a larger, very large x, then it's possible for us to get a very, very large error. So when this x becomes larger, the error becomes larger. So this one, this means, so our linear regression, this is not good. We cannot use our linear regression to estimate something when we have, or prediction some y when the value of x is become large. So in fact, this second example is very, very common when we do the statistics. So when we do especially like data science or other statistic modeling, it's very common for our errors will become larger when we do a estimator to a large x. So we should really, really careful about this second example. And then let's look at the third one. So let's look at the third one. So here was the third one. The third one is, we can see this for our E, the residual is not evenly, right? It's actually very focused in a small region here. And of course, this is also more errors for the positive part and just 1, 2 maybe for the negative part. So of course, this one is also not a good plot. So that means for this plot, if when we plot our residual with respect to x looks like this, then we should say, okay, this means we have some problem of our assumption. Our assumption is not satisfied in this case. So this is how we can use the plot to estimate or to check our assumption 2 and 3 about our error term. And then how about the other thing, like how about the linear relationship? So that means our first assumption here, like our yi is equal beta 0 plus beta y times x plus an error term. So this is our previous videos. We can use the hypothesis test to help us do this. So in our previous videos, we already talk about this a lot. We use maybe 2 or 3 videos to talk about this. So the first one is, of course, we can use the t-test. So we can use the t-test on our beta 0 or beta 1 for it. So if we test our beta 0 equals 0 or our beta 1 is equal 0, then this is some problem. And then the second one is about we can do the ANOVA, the analysis of our variance. And then for this one, in other words, is we can use our t-test. So this is we generally only use this for the two-side test. So for this one, what we will do is we will use this f-test. For f-test is for our beta 1. And then the next thing is this is about our f-test for the beta 1. But in fact, for our ANOVA, in these videos, I will talk this one more way. So this is about the R square. So what is R square here? So let me give the definition for this one. So R0 is just a short name. So in fact, the name is coefficient of our determination. So in our previous video, we already talked a lot about our sum of square, right? So we have the SSE, sum square of our error term, the SSR, and SST. So here, in fact, what we can define is we can define our R square is equal the SSR divided by SST. So by this one, actually, this is a proportion of our variation in the y explained by the regression. So here in our previous videos, of course, we already give the formula for our SSR, SST, but just in case you forgot it, so let me write down this equation here again. So here this is a relationship. So we have the SST is equal our SSE plus SSR. And also we have this equation here. So just in case you wonder this one, so our SSE, in fact, this one is the information of our residuals. So it means here you can see this residuals means the difference between our yi and yi hat. So this is a residual. So this is SS is sum of square, right? So this is sum of square for our residual. And then the SS, the next one is about our SSR. So SSR here is the one about our variation. So this is variation in y explained by the regression on x. So here you can see this is sum of square for our difference between the yi hat and x and yi and y bar. So this is our sample mean of our y. Okay, and then the next thing for our SST. So here for SST, this is generally called this is our total variation here. Okay, so this is our SST. So this is a formula for our R, and also because our SSR is about the variation, right? So that's why when we say the R square, we can say this is a proportion of our variation and divided by our with respect to our total variation here. Okay, and then if we compute this R square, then how we can explain it? For this one, we can use this one. Of course, we say we can use this one to check our assumption 1, right? So assumption 1 is we have a linear relationship. So here what we will have is if we have the value of our R square is very, very large, then we can conclude this one is very close to a linear relationship. So this is how we can have. So here, in fact, this if we have a larger R square, it means we have compared with SST, we have a very large value of the sum of square for the variation. So in other words, the difference between our yi hat and y bar is really large. Okay, so this is how we can use R square to check the linear relationship. So now let me use one example to explain it. So let's look at this example. So now we have the data set. So here we have 5 piles of data. So this look inside these tables. And then just for short, here for this example, I'll give you some more information. So the first one is s sub xy. Second is about the sum of the square of our y. The third is our sample mean of y. So the question is ask us to find the y square. So to find the y square, what we should do is we should, of course, one way to do this is exactly follow our table or the formula before, right? We compute about our SSR for the numerator and SST for the denominator. And then for both of them, it will be we need the estimator of our y hat. And then for this one, what we should do is for this one, let me give you one more information here. So our estimator of our beta 1 is equal 0.49. So this is one information of our estimator. So then to compute our SSR, for this one, of course, there is one way is we just use the equation. It's the difference between our for this one is the difference between our y hat minus y bar. And if we use this one, it means we will need the estimator of yi. In other words, we will need our beta 0 hat plus beta 1 hat times the each value of x. But here, in fact, what we can do is in our previous video, we also say this one we can use another formula. So this our SSR is also equal our estimator of our beta 1 times s sub xy. So in other words, for this question, what we can do is we can directly plug in our value of our beta 1 hat and s sub xy. And then by calculator, we can compute this is 7.84. Okay, this is how we can compute the SSR for short. And then for SST, what we do is, of course, we can use the previous sum of our yi, sum of the square for yi minus y bar. But also in our previous video, we say this one is also equal our sum of yi square and minus n times y bar square. So we also use this equation in our previous videos. And then when we do this one, so we can directly plug in our equation here. So what we do is we can use 30 minus 5 times 2 square. And then by calculator, we will have this is equal 10. So now this is our numerator and denominator. And when we have these two, what we can do is we can compute our r squared, right? So r squared, we can just plug in this two value here. And the answer is 0.784. So then this is our value for r squared. And just let me give one more step here, which is not required by this question. But if we look at this value of our r squared, then what conclusion we can have? So we can conclude our models will account for like 78.4% of the variation of our y in the data. So in other words, like normally or generally, then 78.4% of the data will very close or on our line of our regression model, and others maybe will out of this line. Okay, so this is about how we can compute our R. So of course, if you use our formula we give in the previous page, of course we can compute this by the data side. But also we can, if we have some more information here, then we can use much shorter equations to compute our R square. and also I explain how we can do this conclusion about this one. Okay, so this is about the materials, how we can check the three assumptions of our linear regression. And then now our next videos, I will talk a little more about the correlation of our x and y. And then let's see, please subscribe my channel, and if you have any questions, just leave it in the comments, and see you in my next video.